you will find all the coefficients alpha i's and beta i's, because this is the target we need, and this is the rational approximation to the original function by reserving the first r plus n plus 1 terms. Sorry, I don't think there is a slide on this topic. So based on the algorithm, I have written a Matlab function like this. Paddy function approximation, where C is the coefficient of tensor series expansion of the original function. And you specify the orders of numerators and denominators, you will find the polynomial coefficients of them. So, and this is the function call we need. If you are using this function, you can easily find the Paddy approximation to the original given function. And here is an example. You can find the Taylor series expansion first, and then you can call the original function Paddy approximation and find different orders of approximation and see the results. The original function is something like this, and I think this one is the Paddy approximation of order 1. And the rest of the functions seem to be very close to the original function. Paddy approximation is always very useful, especially in delay control systems. So I will explain more here. Suppose there is a transfer function of the original model without a time delay, and here is a time delay, and here there is a GC controller. In feedback control, you will have system like this. And this kind of system can only be analyzed using simulators or using simulation method, because this part cannot be expressed by a transfer function. So this part can be expressed by a transfer function, but the closed loop system cannot be expressed by a transfer function. So what we normally did is to replace this one. This one should be minus. If we replace this one by a rational function or transfer function, then we can solve this problem easily. Approximation. Yes, you can use Paddy approximation. Otherwise, you cannot find a closed loop system if there is a time delay in the open loop. Alternatively, you can think something like this. If there is a time delay, then the closed loop transfer function should be something like this: g e to the minus 1 plus g c g e to the minus ts. This is no longer a transfer function. So if you are using Matlab, if you are using feedback function, this one will not work, since there is a time delay in the open loop. However, you can solve the problem alternatively like this. You can approximate this one by a transfer function and leave this one alone. So finally, you should get a transfer function representation like this. So this one is an approximation to the original problem, and you can handle a standalone delay.
So leave it like that?
Yeah. In Matlab, if you use TS function, you have to specify n and d, and also you can specify I/O delay equals to t. This is an acceptable Matlab object.
So the problem is using the delay on the denominator.
Yeah.
So that's why
you cannot solve it using feedback function because they had a different time.
we can leave it in the.
You can leave it like this because in Matlab you can specify a transfer function object like this. So the rest part are rational. There's no problem. And also for this part, you can alternatively represent it like this one. So sometimes you have to use Paddy approximation in control system analysis. The equivalent transfer function representation should be something like this. And you can leave the delay out of the loop. Normally, if you select the Paddy approximation of degree 3 by 3, it will get quite a good approximation to the original problem. So Paddy approximation are sometimes useful in delay systems. The key point is how to find a rational approximation to the original function. And for this application, we can use Paddy approximations. So this one is not quite related to the lecture, but it is useful in control. Now let's consider another problem. This is one of the examples. If we have obtained by experiment a set of data like this, and we know that the original function could be of this form, but we do not know the exact coefficients or other values in the protocol function or the prototype function or something like that. We have the data and we have the protocol form of the function, but we do not know details of the coefficients. How can we find from this data the undetermined coefficient? This is very useful in engineering. For instance, you know from, suppose this is a transfer function. We do not know the coefficient in the transfer function. In system identification. If there is a stack input, then we know, suppose if this one is a second order system, then we know the output should be something like C1 e to the minus A1 t plus C2 e to the minus A2 t of this form. We know this form. And we do not know the particular values inside this equation, C3. We will know that the standard form of the system response like this. So what we need is to use the experimental data to estimate these values offline, not online. Not online is online system identification. This one is offline. So how can we solve this kind of problems? So this is an example of system identification of similar things.